time, I defined what a preflow is. It looks a lot like a flow. You have an assignment of values to edges, and they have to satisfy the capacity constraint. But the conservation constraint is now violated. You can put more into a node than you take out of it. Okay, and then the excess. What was that? What was that notation? For excess EFV. EFV is equal to what you flow in minus what you flow out. Okay, out of E. Okay, and so yeah, you flow in 10, you flow out 6, and you lost 4 somewhere. So I suggested last time that perhaps a better term for this would not be excess but loss. But anyway, that's what this notation is defined as. And then obviously, if we have excess equal to 0 everywhere, then we just have we have a normal flow, as we're all familiar with. And the algorithm is going to maintain a preflow throughout. And then at the very end, it's going to have a flow. And we'll see that at that point, it'll in fact be a max flow. It'll be a consequence of something that happens in the algorithm. Whereas in the Ford-Fulkerson algorithm, what happened is you always maintained a flow, but it was only at the end that you had a maximum flow, that the conditions for a maximum flow were satisfied. So in a sense, you have these two things that you're trying to achieve during any algorithm for max flow. One is that you actually have a flow, and the other one is that you satisfied some conditions for when a flow is maximum. And the fact that you have these two different conditions means that you can work on them in different orders. This algorithm maintains the condition for optimality always, and I'll show you that in a minute, but doesn't always have a flow. So when it finally does, then it's a maximum flow, whereas Ford-Fulkerson does it in the other order. I'm emphasizing this because, in fact, in the max flow problem is, in a sense, a special case of linear programming. And in linear programming, you have the same situation that occurs. You have conditions for feasibility and you have conditions for optimality. And you have many different algorithms that trade off how they're making progress on those two conditions. And when you finally get feasibility and optimality, both of those conditions holding at the same time, then you're done. And that's sort of a way of forming a taxonomy of many different linear programming type algorithms. Okay, so the other thing I defined last time was this thing called height. And this is just going to be a number greater than or equal to 0 that's assigned to each vertex v. So I haven't really said much about it. And I think that's where I stopped. Okay, so the next definition is that an ST flow, preflow F, and labeling, I don't know, labeling or labelings H. So H assigns a number to each vertex. So I guess I should call that a labeling as opposed to a labelings. A labeling H are compatible if what? If the following conditions hold. One, first of all, H of t is going to be 0. That's a required condition. H of s is equal to n. Okay, it's really unfortunate that n and h's look so much alike. N is the number of nodes. Okay, and h is this height thing. So let me emphasize n equals number of nodes. Okay, so if ever there's something up here that kind of looks nonsensical, it might be because of a confusion between h's and n's. So try that out. H of s is equal to n, all right? And the most important, for all VW, contained in EF, E little f, and that means in the residual graph, what residual graph? I didn't say anything about a residual graph, but now I will. Even in a preflow, you can apply the same rules for a residual graph as we did in a flow. We just look at an edge. If it has non-zero assignment f to it, where is it? Then we create the back edge with that residual capacity. And if f is less than its original capacity, then we have a forward edge with the difference of the original capacity minus this f value that's associated to it. Yeah?
So the notation EF is the residual graph is really kind of the same thing as GF. It's just using.
Yeah, GF, I don't know where the book changed this. GF is the residual graph, and it consists of vertices, which are the original vertex set, and then an edge set, which is noted by EF. And so these are the edges in the residual graph. Okay, GF is notation for the graph. This is notation just for those particular edges that are in that graph. Yeah?
ST preflow, what is that? F hard?
This word?
No, the first line.
Okay, an ST preflow, F, and a labeling H. Okay. And a labeling H are compatible if well, I'm not quite finished. We have these two conditions and we have half of this condition. For all those edges which are in the residual graph, what's required there is that H of V is less than or equal to H of W plus 1. Okay? So let me just, again, draw a little picture here. So if this is in the residual graph, okay? So F is a preflow now, but you can still define a residual graph with respect to F. If this is an edge in the residual graph, then if, let me just say the height H of W is equal to, let's say, 15, then what this requirement says is that H of V has got to be less than or equal to 16. Okay? It could be strictly less than 15, but anyway, it can't be bigger than 16. H of V less than or equal to H of W plus 1. So the labeling H is compatible with a particular preflow if in the residual graph, the edges that are in the residual graph are not too steep. If you think of these as heights, and they're trying to encourage you to think that way because of the water flow analogy, then they want to say that edges in the residual graph should not be terribly steep. They can actually go uphill, okay, according to that, but they can't go extremely downhill. All right. I mean, mathematically, I understand all this. I don't get the physical analogy, frankly, but a lot of people talk about this algorithm in that way. So, all right. So that's the requirement for compatibility, and we'll technically that'll be a very important condition that's maintained throughout the algorithm. Okay. So now I can actually prove something. With all these definitions, I can actually say something of substance. If F is an ST preflow, then there is no ST path in the residual graph. Okay? So just thinking back in terms of Ford-Fulkerson, in Ford-Fulkerson algorithm, we always maintained a flow as we were going along, and there was always an ST path in the residual graph until the end. That was the termination condition. And it was also the key to proving that the flow at the end of the Ford-Fulkerson algorithm was in fact the maximum flow, if you remember how that proof went. So the fact that there was no ST path was the key, because we then looked at the ST cut that consisted of all the nodes that were reachable from S in the final residual graph, and then T was the remainder. The other side of the cut was the remainder of the nodes. Okay? So I'm going to prove this in a minute, but I'm just pointing out that this was precisely the condition in Ford-Fulkerson which allowed you to say that the flow was maximum. So it was the optimality condition. So this goes back to what I was saying about 5 minutes ago, that in this algorithm, it maintains the optimality condition throughout the entire algorithm, but it doesn't maintain the feasibility condition. Feasibility meaning that you actually have a flow and not a pre-flow. Whereas in Ford-Fulkerson, it was the opposite, the other way around. Okay, so F is an ST pre-flow, then there's no S to T path in GF. Oh, I guess I should have left. Well, that's a true statement about the algorithm, but we can't prove it yet because we don't have the algorithm. I need to put in something more. If F is an ST preflow and H is compatible with F, yeah. So that's what I can prove at the moment. If we have in our hands an ST preflow and we have in our hands a label H which is compatible with it, then there will be no S to T path. And then when you see the algorithm, you'll see that it always maintains an ST preflow and it always maintains a compatible H, and therefore what I was saying about the maintenance of the conditions for optimality makes sense and is true. Question?
So the H that you're talking about there is the height. It's all H's. I mean all heights, right? So it's such
Yeah.
that any BW is one part, or is that most? I mean that formula. Right?
Yeah, right. H is this labeling, this mysterious labeling. All I've told you about it so far is this. And then I've said to be compatible, it has to have this condition. Okay, but I didn't say where this H comes from yet. But I'm just saying if we have one, if we have a compatible H and we have a preflow, then you can't have an S to T path in the residual graph. Okay, so let's prove that.
I have a question.
Yeah. Okay.
Okay, so can you think of a free flow as like an intermediate condition before it reaches optimality?
Yes.
Okay.
I mean, that's, well, I mean, it's an intermediate condition of the algorithm. It's not an intermediate condition of anything physical that I can think of. I mean, the flow makes physical sense. Preflow, I guess preflow sort of makes physical sense too, because, yeah, it's just like a flow with some leakage, some losses at nodes. Okay, so you can think of that physically, if you will. But in fact, no, that physical analogy is not good if it actually loses liquid at a node. It has to just build up at that node. It has to actually not disappear. It's just stuck there. Okay, so it's more like traffic than okay. Anyway, I'll just do this mathematically and not rely on the physical analogy. Okay, suppose not. Suppose there's a preflow F and a compatible labeling H, and there is in fact an ST path. And here's one from S to T in GF. Okay, well, this is a compatible, the labeling is compatible. So what's H of T? Yeah, it's 0 according to what that says. So here's H of T is equal to 0. And H of S is equal to N. Okay? All right, so this is smaller than this. Okay? These are edges in the residual graph. That's what we're saying. This is a path in the residual graph from S to T. So each one of these edges is a residual graph. So what can I say about the H of this node? So H of V What do I know about it? It's at most what?
At most 1.
It's at most 1 because by compatibility, h of v has got to be less than or equal to h of w plus 1. At the moment, w here is t, or t is w. Anyway, this tells us that the h of this v is at most 1, right? Less than or equal to 1. What about this node? It's at most 2. Okay, h here is less than or equal to 2. And you go up. So following this chain backwards, how many nodes? This is h of 1, 2. How many nodes are in here? If we go that way, that's n minus 1 nodes. So that chain of reasoning says h of s is less than or equal to n minus 1. Okay? But we know that h of s is equal to n. So that's a contradiction. So again, by supposing that there is actually a path from s to t in the residual graph, we get that h of s must be less than or equal to n minus 1. But this h labeling was assumed to be compatible with f, and therefore h of s is required to be n. And that's a contradiction. So it must be that, in fact, there is no s to t path in the residual graph. All right, so that's the proof. All right, and so the algorithm is going to maintain a preflow, and it's going to maintain a compatible labeling, and therefore, when the algorithm finally gets to be a flow, we're going to have this situation maintained because it was maintained throughout, and that's going to tell you that the flow is in fact a max flow. Why is the flow a max flow at that point? Because it has exactly the same termination condition as Ford-Fulkerson. I mean, at termination, we have a flow, and we have no S to T path in the residual graph, and that's precisely what we used to prove that the Ford-Fulkerson max flow is in fact a max flow. So exactly the same logic applies. Yeah.
So how do you know when you terminate, when you have the flow with this, is when there's no excess capacity?
Yeah, and you know you have flow when there's no excess capacity. So that's going to be the termination condition. No excess flow, when, not excess capacity, excess here, EFV is equal to 0. Okay, for all nodes V. All right.
But you never have a ST path in the residual graph during this algorithm.
That's right. This is, well, if the algorithm maintains a compatible H, and we'll need that in the algorithm too. Of course, I haven't shown you any of the details of the algorithm. This is all so far just, in a sense, warm-up advertising, although this is a theorem. This is certainly something we've now proven, that if we have a preflow F and a compatible H, then there's no S to T path in the residual graph. Okay, so now we have to delve into the details of the actual algorithm. Page 10. Okay, so the algorithm is called Preflow-Push, and therefore there are two procedures. One is called push, and the other is called not called preflow. The other one is called relabel. Okay, so these are, and then the algorithm itself is going to be working between those two. So the way I'll do it is I'll show you what a push is, I'll show you what a relabel is, and then I'll put them together. So it's a bit, hopefully as I lay out the algorithm, some of it will mean something to you, but there's a little bit of just detail here before it might. Okay, so this is a push. We have a flow F, we have a labeling H, which is compatible, and we have a two nodes, V and W. All right, so if V has some excess, greater than 0. So what's the push? The push is trying to do is get rid of excess from V. If V is a node that has some excess in it, the algorithm is trying to get rid of it. And how can the algorithm get rid of excess at a node? It can either push it forward to some other node, or if it has excess, it can push it backwards to some node that gave it the excess. Okay, or some node, anyway, it can push it backwards against some flow that was into V. So if it has excess there, and we have this other requirement satisfied, HW less than H of V, okay? Well, what does that mean? That means that the height of W is less than the height of V. So we're going to be pushing downhill, if you want to keep that physical analogy. And VW is contained in EF. So this is actually, from V to W, there's a residual edge. Now, we don't know whether, in this, so far, I haven't told you whether VW is a forward edge or a backward edge, just that it's in the residual graph, okay? So here from V to W, it's in the residual graph. Okay, so we'll do the two cases. If E is VW is a forward edge, okay, then delta, it's the minimum of EFV, or CE minus FE, then increase FE by delta. Okay, so what's this saying? You have some excess at V. Got more flow in V to V than you have out. So you'd like to get rid of that, either pushing it forward or backwards. So this is the forward. If V to W is really a forward edge, so that really is that edge there, you can either push out the entire excess that's there, or you can push out that amount, whichever is smaller. I mean, you can't push out more on an edge than you have additional capacity for. So this is the amount that you can additionally push along the edge from V to W, and this is the amount you would like to push. So whichever of these is smaller, we're going to push out that amount on E, and that means that we're going to increase FE by that delta. Okay? And the other case is the backward edge. If VW is a backward edge, so here's this is the edge in the residual graph, but it meant that this was the original edge in G. The original edge went from W to V, right? If VW is in the residual graph and it's a backward edge, then the original node we're talking about, the original edge we're talking about, goes from W to V. Okay? And again, we're going to define delta as the minimum of the excess at V and the flow along E. Okay, but now E is equal to WV. It's the flow along that edge, and the excess is still at V. Okay? And then we can decrease. Now, I'm going to put these two statements together. Decrease F of E by that much. So we're going to decrease the flow that goes from here to here by as much as we can. If the flow here is bigger, if the flow along here, let's say it was 25 units went from here to here, and you have an excess of 10 here, then you can decrease this flow to 15, and you've taken care of the excess. On the other hand, if the flow here, let's say, is 25, but the excess is 40, then you can only decrease the flow in here by 25. You can't get a flow of 0 or a preflow. Preflows, all right. And then in either case, you return the new preflow H, F, and you return the labeling H. Actually, you didn't do anything to the labeling H. That's just a formal thing. So labeling H didn't change at all here. Input was a preflow, a labeling, and a particular VW, and if that VW satisfies the conditions that it has excess and VW is in the residual graph, those are natural conditions for doing something along that edge. This one is the one that's a little bit mysterious. Why do we have that in here? But you'll see that that's actually very important. Okay, so I said that was one of the procedures. And what's the other procedure? Well, it's a relabel. So far, we haven't touched H. H was just this mystery labeling, and we don't know anything more about it. Now we will. So relabel F, H, and V. So if E, FV is greater than 0, and for all W, it's all VW contained in EF, H of W is greater than or equal to H of V. And so what does this mean? You've got excess at V, and you'd like to push it out, that excess somewhere. You'd like to push it somewhere to some node W. But the only edges you're allowed to use are the ones that are in the residual graph, according to the push rule. And you're only allowed to push from V to W if the height of V is greater than the height of W. So this is saying you're stuck. Okay? There's no way to push out of V, because for any VW residual edge, and maybe there isn't even, maybe there aren't even any, but anyway, if there are even residual edges, you're stuck because the labeling is wrong. So what do you imagine you want to do? To get some additional opportunity to push out of V, you'd like to relabel something here because something's wrong. Okay? I mean, something's at least undesirable. I don't know about wrong. And then it's if those conditions hold, then increase. Let's just say H of V gets to be H of V plus 1. Okay? So we're going to increase the labeling on V. We're going to raise it up, make it a little steeper, make this edge a little steeper. Okay? In fact, make other edges steeper. Whatever is connected to V, V is going up, so those edges out of V in the residual graph are now steeper. Okay, and then we're going to just return the F and H. So this procedure doesn't touch F, it just touches H. That procedure touched F and didn't change H. And these are the two procedures of the algorithm. Okay.
Why is it always legal to increase H of V?
Why is it always what?
How do I know that I can increase H of V and still keep compatible F and H?
Okay, so the question is, I'd advertised that we're going to maintain compatibility, but now I'm playing around with these H's, and over there I was playing around with F's, which changed the residual graph. How do I know I'm going to maintain compatibility? Well, we prove it. We prove that we will, which we'll do next, probably. Okay, well, first I have to tell you what the whole algorithm is. I'd really like to keep the definition of compatibility, because this one is the key one, and I always get confused which direction this is supposed to go, particularly because we're going to start changing V's and F's. What used to be a V now becomes a W, and anyway, so I'd like to keep that up there. And here's the whole Preflow-Push algorithm. So this is initialize we start out with h of v equals 0 for all v not equal to s, and h of s equal to n, right? That's how we started out. And then f of e is initialized to its capacity for all, or maybe I should say for any and all are really difficult words in English. Anyway, for any e contained in SV, equal to SV, I probably should say. Okay? And f equals 0 otherwise. So what this is saying is the way you start out the algorithm, first of all, you have this labeling, but you start out with the following preflow. Here's S, here's T. All of these edges in here start out with a preflow of 0, but each one of these edges starts out with a preflow equal to their capacity. So if this is like 5, then F there is going to be 5, and so on. So whatever is its capacity of the edges that's out of S, we're going to set the preflow value equal to that capacity. Now, is this a preflow? Sure. What goes into each node is greater than or equal to what goes out of it. And because everything over here is 0, but these nodes are actually getting something. And the value assigned is between 0 and its capacity. Well, these are set to its capacity, so that's fine. These are set to 0, so that's fine. And is this a compatible? Initially, is this H compatible with this F? Well, look at the definition of compatibility. H of t is 0, that's true. H of s is equal to n, that's true. And for each VW that's in the residual graph, we have to have this relation. Well, what's in the residual graph after this beginning? What's in the residual graph, so this is GF, is in S, we have all these edges going backwards. We have no forward edges because these are already, the F was put at its capacity, so these are all backward edges. And then you also have the original edges that do not touch S. Okay, T is over here. So are we satisfying the conditions for compatibility? So this says that if you have an edge from V to W, who's V and who's W? Here's a V, here's a W, right? This H should be less than or equal to this H plus 1. Okay, well, this is N, and this is H of N, and this is H of 0. So certainly this H is less than or equal to N plus 1. 0 is less than or equal to N plus 1. And then the ones over here, well, they're both equal to 0, so their H is both equal to 0. So we have initially compatibility. Okay. But the general step is this. General step is, that was just the initialization. While there is some V with excess, EFV greater than 0. So some node has excess. I guess I better say that's not equal to T. Okay. I don't know how well this shows up on the TV, but anyway, V not equal to T, because T can certainly have excess. It can have more into it than out of it. Well, there's no way out from T. You check in, but you don't check out. Okay, V is in T, and it's such that. So for V not equal to T, so this node has some excess. If there exists a W such that push VH, FH, VW is possible, then, well, do it. Push from VW. Do that push. So if you can ever get rid of some excess somewhere, go ahead and do that. But if you're stuck and you can't do it, well, actually, this is for a particular V. So you take a look at a V, and if you can push out a V, that's fine. Otherwise, else you relabel F and V. Is that what I have? Yeah. Well, relabel has FHV. Okay. And then this while ends, and you just return F. Okay? So all you're really doing is you're always trying to reduce excess. You start out initially by producing this excess of all the nodes that are adjacent to S. Okay? Those guys all have excess. And then you're trying to get rid of that excess by grabbing one of them. There's a node that has some excess, and pushing. Pushing means, well, if I can go forward, then let's do so. Otherwise, let's go backwards. Okay? And if I really can't do any of those, either of those for that node V, then let's relabel V and see where I'm at. Okay? It's a very decentralized kind of algorithm because it's not like the Ford-Fulkerson where there's always this continuous path. You know, this algorithm is just grabbing nodes all over the place that have any node that has some excess. Let's try to do something about it. And if we can, then we'll push. If we can't, we'll relabel. And then you grab another node that has excess. We haven't said anything about which nodes. Any rules about which node we're going to grab that may have excess. You know, if we grab this node and we push something forward, then this has excess while these guys still do. But we haven't yet said anything about those rules. Yeah?
I have trouble seeing the excess in the nodes and the residual graph after the initialization step. Because you've moved you've taken all the capacities out of S and shoved them into the first node.
Right.
If you do the residual, you'll have, as your graph is showing, then it doesn't look like there's any flow going into those first nodes. It's only flow going out.
Well, that's in the residual graph, yes. All the edges got reversed.
Right.
All those edges that got used got reversed. But the flow is just an assignment of F values. Those don't change by just constructing the residual graph. They only F only change after we do some pushes, after we do a push. So the excess that's at a neighbor of S is still there even when we form the residual graph. Now, if we push backwards all of it, then it would, you know, but then, yeah, then it's going nowhere. But if you look at here over the push, what about it? If it's a forward edge, then you do that. And if it's a backward edge, then you can do that. So we're going to need some rules that say later on that this is, you don't want to just push everything back to S initially. Okay? But right now, this is what the algorithm is. You have access at some node, and you try to get rid of it. Okay? It's the hot potato algorithm. I mean, imagine this water is really hot, and you've got to get rid of it. And so you push it out what you can, or you raise yourself up so that you're more likely to push something out. That just reminded me. I was told that our tape, there's a hissing sound on it that they're trying to figure out about where it comes from, or a periodic buzz or something. And they thought it was because they thought it was coming from my phone, but I don't have it. I do have a phone, but I don't turn it on. So if anybody has a periodically buzzing sound, that's, you know, try to turn that off. Okay, so that's the algorithm. Let me prove one. I mean, we're going to change some of the implementation details. But the next natural thing is to argue that throughout this algorithm, it's always a preflow. And throughout the algorithm, it's always compatible with H. Okay, why is it always a preflow? Well, that should be pretty simple. In preflow, how are we changing F? We're only changing F in these rules. Okay, and it's changing the F on a single edge either by pushing more in the forward direction, but never more than its total capacity. And it's pushing backwards, but never so that it becomes negative. So we're always maintaining an F assignment that's between 0 and its capacity. And to be a preflow means that there's more coming in than going out. Okay? So we can prove this by induction, that this is always a preflow. Suppose you have a preflow, and now you push in a forward direction. Okay? Well, you're pushing from V to W. Well, that's increasing what's at W. So it's the rule that says that it's getting more in than out, or greater than or equal. Anyway, what's coming in is greater than or equal to what's coming out. That's certainly okay because it was true before, and now it's getting more. So that's certainly true. What about this one? Well, what we said was it was getting more in, or the amount in was greater than or equal to the amount out. Now we're pushing some out, but only what was there, only the amount that was in excess. So it again is going to maintain that condition that the sum of what comes in is greater than or equal to the sum of what goes out. That's fine. If it's a back edge, then again, well, I'll let you go through that case, but again, you should see that the conditions for preflow are maintained. Okay, now the conditions for compatibility, that is a little bit more subtle, or anyway, it takes, anyway, let's do it. I want to maintain time for passing out the homeworks, but let's try to do compatibility. So compatibility is a condition between the flow F and the labeling H. So again, by induction, we already said at the very beginning we have compatibility. So we'll do this by induction. What changes? Well, we change H when we relabel, okay? And we change flow over there by pushing, which also changes the residual graph, which can change the residual graph. So what can happen when you do a push? What can happen when you do a push is an edge that had been in the residual graph can now disappear. If you push in the forward direction, that edge that had been there can now disappear. Okay? If you push in the backwards direction, that edge might disappear. Okay? Disappearing edges don't ever cause contradiction to compatibility because that only applies to edges that are in the residual graph. But you can also create an edge when you do a push. How do you create an edge that wasn't there before? If this is a forward edge, and from F to W, that's forward, and its flow is 0, then the backward edge isn't there. But now you push, and you create a backward edge. So pushing can create additional edges. But now we'll want to make sure that the relationship of the HW and HV is correct. HW, HV. Now, this is where things start getting confusing because the condition for compatibility said HV less than or equal to HW plus 1. But this V and W were in that relationship. Okay, I should have just made this P and Q. Okay. P and Q. All right, so we did a flow from P to Q, and now we have this back edge from Q to P. We want to make sure that we've satisfied the compatibility. So this Q is now playing the role of V, and P is now playing the role of W here. Okay? Now, do we have this relationship? H, so we need in particular that H of P is less than or equal to H of Q plus 1. Do we have that?